Okay, for lesson 4.3, we'll deal with this in actually over 3 days, but for our first day, a homogeneous linear differential equation with constant coefficients. That's the big difference. We've already dealt with some differential equations where we didn't necessarily have constant coefficients, but let's address that today. We can consider a first order linear differential equation, y prime plus ay equals 0. We can consider the second order differential equation, ay prime plus by prime plus cy equals 0. If a, b, and c are constant coefficients, what we're going to do is have the following method. Assume a solution is of the form y equals e to the mx. And if that's true, y prime equals m e to the mx using a chain rule. Y double prime would be m squared e to the mx. If we were to substitute those in to this original differential equation, our y double prime is m squared now, e to the mx. Here we have a b, but our y prime would be m e to the mx. And then we'd have plus c times y, but we're assuming that we'd have e to the mx equals 0. Tell you what, e to the mx is a non-zero quantity, so we could divide by e to the mx everywhere. And what we will be left with will be am squared plus bm plus c equals 0. This is what we will get, a quadratic equation in M. This is called the characteristic equation, or of course a differential equation. Now, by the way, it's very reasonable to make this assumption even if we went back to our first equation. The reason why we had a little bit of space is you might be able to solve that and find that it is in an exponential form. It's very believable that a second order, or perhaps even higher orders, might involve e to the mx. So it's a very reasonable kind of an assumption. But when you have a quadratic, if we solve any quadratic, of course we will think about solving. Normally we were solving ax squared plus bx plus c. You very quickly will recall from Algebra 2, even in Algebra 1, honestly, the quadratic formula. The quadratic formula wonderfully will solve any quadratic equation. And what we're going to do is consider the discriminant. The discriminant is very simply the argument of the radical. And just highlighting what's happening with this discriminant, if b squared minus 4ac, if that inside of the radical was greater than 0, we'd get 2 real solutions. If b squared minus 4ac was 0, well, that whole square root would collapse down to 0, and we'd get 1 real solution. And then finally, the discriminant allows us to say if b squared minus 4ac is less than 0, of course then we have a negative value inside of our square root. We would get 2 complex solutions. Well, keeping all of that in mind, case 1 would be where, hey, let's consider that our discriminant is positive. We'd get 2 real solutions. Let's just say you work out the quadratic formula and you get 2 distinct values for m. Remember, we're solving this original equation up at the top, not with respect to x, but with respect to m. We'd get m equals those 2 real values. So we could call them m sub 1 and sub 2. But remember, we're assuming that our solutions are y equals e to the mx. Our general solution would, of course, have to be then involving e to the m1x and e to the m2x, writing arbitrary constants out in front of them, adding them together. That's our superposition principle. Case 2, as we look at this, what happens when we get one real solution? Well, one real solution, you can see from what we've written down here, this would be case 2. Well, my goodness, for case 2, that's assuming that our discriminant were equal to 0. Now, look back up to the quadratic formula. If that argument of the radical was 0, if b squared minus 4ac were to equal 0, m would have to equal opposite b all over 2a, because that whole radical would disappear. You'd have opposite b plus or minus 0 all over 2a. So that would be your one real solution. And very quickly we could come up with y sub 1 equals e to the m1x. However, you might expect that we would have two linearly independent solutions, like we've been talking about earlier this week. Just yesterday, we developed a formula to find the other solution. And what we'll do is we'll use this idea right here where, that formula from yesterday was y sub 2 would equal y1 times the integral of e to the opposite of the integral of p of x dx divided by y1 squared. And you might wonder what p is in this regard. Well, remember, p would be coming from our differential equation that we'd be working with. And if we went right back up to this first form, remember p had to come from the form where we have a 1 for our y double prime. So if I divide by a real quickly, we would have this. This would be our p of x, and over here would be our q of x. Not that we need that. But p of x is b over a. Well, look what's happening now. We can say, look at this. The p of x is going to be b over a. And there we have it. And down below we have e to the 2 m1. But, hey, what did we say m1 was? Hey, look at this. m1 was opposite b all over 2a. So if we were to just continue this out, we'd have e to the m1x, integral of e to the opposite of b over a, and actually if we work that out, take an antiderivative, we'd get very simply opposite b over a x, wouldn't we? And down below here we'd have e to the 2 times b all over, or opposite b over 2a. Look at that, the 2's cancel. Wow, these numerators and denominators would cancel out. I hope you can see that very clearly. Down below, when you have e to the 2 times opposite b all over 2a, the 2's are gone, but now your numerator and denominator are gone. So what's left? Just a 1. What's the antiderivative of a 1? An x. So pull that out, and my goodness, would you look at that? That's where this second solution occurs. So we have e to the m1x, y2 is x times e to the m1x. Here are your two general solutions added together. Real quickly, let's take a look at the complex solutions. If your discriminant is negative, you would get complex numbers, a real plus an imaginary. And my goodness, that can look intimidating at first glance. What we need to do is realize that it's always e to the m1x and e to the m2x. So what seems intimidating at this point is the fact that our m's are complex numbers, and we look at that and think, wow, I could at least separate this as e to the alpha x times e to the beta ix and do the same thing for y2. But that imaginary component probably seems a little bit intimidating. Well, Euler did some great work showing that e to the I theta is equal to the cosine of theta plus I sine of theta. Also, some reminders. Cosine is an even function, so the cosine of the opposite of theta equals the cosine of theta. And similarly, the sine of the opposite of theta equals the opposite of sine of theta. Now, why are we bringing this up? Well, just to show you that we could definitely now take a look at what's happening with e to the bix and e to the opposite bix. Following this formula, or beta I should say, e to the beta ix would equal, according to what we're seeing here, cosine of beta x plus I sine of beta x. Similarly, e to the opposite beta ix would equal, now remember the cosine of an opposite beta is going to be the same thing as just the cosine of it, so we'd get the cosine of beta x. However, the sine of an opposite angle, that negative is going to come out. So that's why we reviewed that other part. So here we have e to the beta ix and e to the opposite beta ix. What I want to do real quickly is pull two ideas together for you. E to the beta ix plus e to the opposite beta ix. Add these two quantities together, and you'd see that the imaginary components are going to cancel out, leaving us with 2 cosine of beta x. Why we're doing that hopefully will become clear in a moment. What else? We could see that if I wanted to subtract e to the beta ix minus e to the opposite beta ix, well, distribute a negative to this e to the opposite beta ix. Now you'd see that the cosines would cancel out, and the I sine beta x's would add together. Yes, there's an imaginary component here. It's 2I sine of beta x. So that's just a little bit of preliminary work that we're going to use. We're going to extend this now. And going back to this basic idea of a superposition kind of a principle, we could say that go to your y1 and y2, and we'd have a general solution saying that we'd have a constant 1 times, take your y1, but let's separate it, e alpha x, e beta ix, and then we'll say plus, have a constant 2 times y, and that y2 can be written in a similar format. We could say e to the alpha x times e to the opposite beta ix. And remember, any constants are going to work. So let's just say over here that we want c1 to equal c2 to equal 1. If that's the case, just put 1's out in front there, and this would be our y value. And if that's the case, tell you what, we could factor out e to the alpha x from both of those. What's left? E to the beta ix plus e to the opposite beta ix. That's why I did some preliminary work before. If you look above right here, we did some work as to what occurs when you add those two together. And my goodness, you can see you get 2 cosine of beta x. So this becomes e to the alpha x. This whole thing becomes cosine of beta x. Now, what else could we have? Well, we could have c1 and c2 being opposite signs of 1 and negative 1. And we're going to have to pick that up in just a moment in our next video.